All right, so these are conservation of energy problems, and they are all going to be two to two type problems, right? With gravity, what we're going to say is that in all of the problems, we're going to say that the kinetic energy plus the potential energy is equal to the kinetic energy plus the potential energy, okay? With gravity, this doubles up to 1 half mv squared plus negative g m m over r, right? It's not r squared, remember it's just r, okay? Equals 1 half mv squared at a different time, right? Plus negative, remember that gravitational potentials are negative, okay, over r, okay? So this is what we're about on this thing, right? We're gonna set this thing up. Keep in mind that remember that electrical potentials are positive, right? So if this is an electrical problem, it'll be positive kqq over r, okay? Anyway, let's just see what we can do here. So notice that, by the way, the mass of the rock in this case will actually cancel out, because this is the 5.2 kilograms is right there, and right there, and right there, and right there. Okay, so I like to cancel those. That helps my brain. Okay, so I'm going to go. Let's see. It's orbiting around the planet, so that's going to be this mass. The planet's making a giant dent in the sheet of rubber, right? Okay. At one point in time, it's this with that radius. Okay, so I'll go 1 half 6790 squared plus negative g times 4.8 e24 divided by, and g is, of course, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, right? Okay, so this is a g, this is the fundamental constant, g. All right, 6790. And then that's the distance that goes with this velocity. So 8.4 E6. Okay. And that's going to equal a different distance, right? So it's going to be going 5860. Presumably it's farther away now, right? So 1 half 5860 squared plus negative g times 4.8 E24, right, divided by r, right? So now we're trying to find that r, right? All right, so here we go. From the planet's center. Okay, let's see if we can get this. All right, I guess what I'm going to do is I'm going to do this whole side here. So I'm going to go 0.5 times 6790 squared. Okay, and then I'm going to go minus 6.67 e negative 11 times 4.8 e24 divided by 8.4 e6. And I'm getting a negative number here, okay? And that is because, of course, it's in orbit, right? Negative potentials mean that it's gravitationally bound. Okay, so now what I'm going to do is I'm going to subtract this guy from it. So I'm going to go minus 0.5 times 5860 squared. And now I've got on my calculator what this equals, right? So now I'm going to go negative 6.67 e minus 11 times 4.8 e24. Okay, divided by the answer I just got. And I get R is 9932974.8. My TI calculator very unhelpfully does not put this in scientific notation. So let's see, 1, 2, 3, 4, 5, 6. 9.93 times 10 to the 6th meters. All right. Now let me just say, because I know this. I happen to know this. Okay. Take a careful look at all the ones that are like this I did with the moon. Okay. So this one is very nice because it's just asking what the distance is from the planet's center. Okay. There is the tricky bit of if you've got, say, the moon, right, and we're orbiting some distance like this above the moon. Okay. that you're going to have to do some subtracting, right? The radius of the moon, I'm going to ask you, how high above the surface of the moon are you? You'll get the distance from the center, and you'll have to subtract the radius of the moon. So take a look at the moon problems. Okay, those are the ones that I use when I use gravity questions. Okay, so just keep that in mind. All right, good enough. Happy hunting.